What would it take to build a computer before electricity, electronics, or even the word computer had acquired its modern meaning? In the 1820s, Charles Babbage attempted an answer in brass, steel, and relentless calculation. His difference engine was designed to produce mathematical tables automatically, reducing the errors made by human computers. It was an audacious machine, and its unfinished story became one of the great tragedies and triumphs of Victorian engineering. Charles Babbage was an English mathematician, inventor, and reformer of scientific practice. He had watched errors creep into printed tables used by astronomers, navigators, engineers, and surveyors. A single mistaken digit could send a calculation, a ship, or a scientific conclusion in the wrong direction. Babbage imagined replacing fallible hand calculation with a mechanism whose procedures were locked into metal. The principle behind the difference engine was both ingenious and surprisingly practical. Many mathematical functions can be represented by sequences whose changes follow regular patterns. Instead of repeatedly performing complicated multiplication or division, the machine could add fixed differences from one result to the next. Addition was comparatively manageable for mechanical gears. Babbage intended to make repetition do the difficult work. The idea emerged publicly in the early 1820s when Babbage presented his plan for a calculating machine capable of producing reliable numerical tables. The machine would not think, reason, or understand. It would follow a carefully designed sequence of mechanical steps. Yet that limitation was also its power. By narrowing the task, Babbage made automation conceivable with the tools of his century. The first challenge was scale. A calculating device that handled only a few digits might fit on a desk. Babbage wanted something far more capable, with columns of figures carried through a network of rotating wheels. Each wheel represented a digit, and when one passed its limit, a mechanism had to transfer a carry to the next. The process had to occur repeatedly, accurately, and without jamming. That requirement transformed arithmetic into physical engineering. On paper, a carry was an invisible instruction. In metal, it became a timed movement involving teeth, levers, stops, and stored force. Every part had to move far enough, but not too far. A tiny discrepancy could accumulate across the machine. The difference engine was therefore not merely a calculator. It was a negotiation between mathematical certainty and material imperfection. The British government recognized the potential value of the project and provided financial support. That assistance made construction possible, but it did not make the undertaking simple. Public money demanded accountability, while Babbage's ambitions kept expanding. Estimates, designs, contracts, and expectations collided. The machine existed simultaneously as a scientific promise, an engineering project, and a political responsibility. In the workshop, the central figure was Joseph Clement, a highly skilled manufacturer and engineer entrusted with producing much of the precision work. Babbage supplied demanding designs. Clement and his craftsmen had to turn those designs into components that could actually be cut, fitted, and adjusted. The relationship carried immense potential but also strain. A machine conceived in drawings could become a battlefield once money and workmanship entered the process. Victorian workshops possessed remarkable skills, yet they did not have modern numerical control machines or standardized precision manufacturing. Each component had to be made, inspected, and fitted through laborious craft. The closer Babbage looked, the more imperfections he found. Parts that appeared acceptable in isolation might fail when joined to dozens of others. His standards rose with every discovery, and the project's schedule receded before them. Babbage's perfectionism was not simple vanity. He understood that an automatic calculator could not rely on an operator quietly correcting its mistakes. The mechanism had to carry its own discipline. Still, his insistence on improvement created a dangerous cycle. A design was revised, manufacturing paused, and completed parts risked becoming obsolete. The inventor was trying to achieve certainty in a world built from tolerances. The machine's intended rhythm was mesmerizing in concept. Number wheels would turn through successive values, mechanical additions would be carried forward, and the results could be read as a developing table. Babbage also envisioned a printing arrangement because a calculator that produced answers still left room for transcription errors. The ideal machine would calculate and preserve its results with as little human interference as possible. But every added capability multiplied the burden. A printing mechanism required alignment, pressure, timing, and dependable contact with the calculated values. The engine had to tolerate repeated operation rather than merely demonstrate one successful movement. Its purpose was not to perform a theatrical trick. It was to become a trustworthy industrial instrument for knowledge. Beyond the workshop, mathematical tables formed part of the hidden infrastructure of the 19th century world. Navigators depended on them to interpret the heavens and guide ships. Engineers used them to design and measure. Astronomers and surveyors built conclusions upon columns of printed numbers. Babbage was responding to a widespread problem. Modern science was advancing faster than the methods used to support its arithmetic. That context explains the urgency behind his obsession. The difference engine was not a curiosity intended only for a cabinet of wonders. It promised to strengthen navigation, commerce, science, and government by making numerical information more dependable. Its gears were aimed at a quiet but profound revolution, the transfer of repetitive intellectual labor from people to machines. Yet the project's public importance could not settle private disagreements. Costs grew, schedules slipped, and disputes over manufacturing arrangements deepened. Babbage wanted control over the design and its execution. Clement's workshop operated according to the realities of skilled production, expense, and contractual authority. When trust weakened, the machine's future became entangled with questions no gear could answer. By the early 1830s, substantial work had been completed, but the full difference engine had not reached the finished state Babbage demanded. The government's patience diminished as the project consumed money without delivering a completed machine. Construction eventually stopped. The failure was not caused by a single broken cog or one moment of incompetence. It was the result of ambition colliding with finance, manufacturing limits, management, and time. For Babbage, the interruption was devastating, but it did not end the idea. Instead, his thinking moved toward a more powerful design known as the analytical engine. The difference engine had been intended primarily to evaluate numerical sequences. The analytical engine aimed at a broader form of programmable computation, using operations, stored values, and instructions arranged in a more flexible system. The shift revealed something crucial about invention. A failed construction can still succeed as an act of discovery. While struggling to build one machine, Babbage had exposed the principles needed for another. The workshop's frustrations became intellectual evidence. They showed him not only what could be made, but what a truly general calculating machine would require. This later vision owed much to the difference engine's mechanical discipline. Babbage imagined separate sections for operations and storage, along with instructions conveyed through punched cards associated with automated textile machinery. The concepts were extraordinarily advanced for the period. They did not produce a completed general-purpose computer in his lifetime, but they placed programmable computation within the realm of serious engineering thought. The human cost remained real. Babbage spent years pursuing mechanisms that demanded money, attention, and emotional endurance. He faced criticism from officials and disappointment from supporters. The unfinished engine stood as a physical reminder that insight alone cannot guarantee completion. A brilliant design still needs institutions, reliable production, patient funding, and a team capable of carrying an idea through its most difficult middle. That middle is where many inventions truly live. The beginning is filled with possibility. The end, if it arrives, looks inevitable in retrospect. Babbage endured the far less glamorous territory between them, where drawings resisted metal and every solution exposed another problem. His tragedy was not that he lacked vision. It was that his vision repeatedly exceeded the systems available to realize it, and yet the machine's influence did not depend entirely on its completion. The difference engine demonstrated that calculation could be organized as a sequence of physical operations. It treated numbers not merely as marks on paper, but as states represented by mechanisms. That change in viewpoint helped open a path toward automatic computing long before electrical circuits made such systems practical. The story also illuminates the partnership between mathematics and manufacture. An abstract method, such as calculating through finite differences, can appear weightless and effortless. Babbage forced it into the world, where force, friction, wear, and alignment mattered. His attempt revealed that computation is never only an idea. It is also a material process shaped by the properties and limits of its tools. In later generations, electronic computers would perform in moments what Babbage's machinery struggled to accomplish through motion. Their speed could make his gears seem primitive. That judgment would miss the essential wonder. Babbage was attempting to build the future using the language of his own age. Wheels instead of circuits, punched cards instead of electronic instructions, and workshop craft instead of automated fabrication. The unfinished difference engine therefore occupies a remarkable place in history. It was a machine that never fully became the instrument its creator imagined, yet it helped make a new category of machine imaginable at all. Its partial failure preserved a lesson more valuable than a simple victory. Precision must be designed, manufactured, financed, and maintained as one complete system. Charles Babbage did not finish the difference engine as planned, but the attempt changed the horizon of invention. In its turning wheels, difficult contracts, ruined schedules, and stubborn revisions, the 19th century glimpsed a machine that could calculate without continuous human direction. The gears did not merely chase numbers, they carried an idea forward into the future where computing would finally find the tools to become real.